Hello everyone, my name is Willa. I'm a PhD student from the University of Chicago. Today I'm excited to open a session and present this work, BloomBeacon. BloomBeacon is this modular relocatable device that the users can flexibly place and move. It is compact when active, and it blooms into a large touch surface in mid-air on demand. This compact device supports mid-air display, direct physical contact, and touch sensing. The vision behind BloomBeacon has been long-standing. People have long dreamed of display that emerge on demand, appearing in mid-air and allow interaction, and collapsing when not in use. And in pursuit of such a dream, lots of mid-air display systems have been proposed. Most mid-air displays lack physical contact. They rely on imperceptible particles such as water droplets or fog, where users' finger just pass through them. Or they rely on additional specialized haptic systems such as ultrasonic beams to simulate tactile sensation. Simply put, most mid-air displays do not support direct physical contact. And in this project, we propose a concept of blooming, which repurposes the spinning motion to deploy a large, touchable surface from a compact line. I envision blooming as a flexible way for users to augment their environment. When the touch display is not in use, it is small and compact, almost like a dot or a line, and users can place it on objects they want to augment and only when it is needed, it expands via spinning into a mid-air touch surface. And some part of this technology might be familiar to some of you who have seen those commercial fan displays. These visuals appear floating and popped out from the environment, but none of them are directly interactable by hand. And for our device, the first challenge we need to tackle is safety. To do so, we engineered this device from the ground up and made the blades with soft materials, CPU, and flexible PCB. The thickness, weight of the materials, and the speed of rotation are all based on a physics model we derived for safety assessments. These have allowed our device not only safe to touch the surface, but also safe to reach through. And notice that the surface electrodes are arc-shaped. These arcs are essentially a touch buffer that allows your hand to touch something soft and deformable without having to touch the spinning elements itself. And our device also detects external resistance such as hair and can auto stop and resume. And last but not least, it can perform touch sensing. It detects the touch location on the display. So let's talk about how I implement it. Here's the basic architecture. It has a motor, an LED blade, and the sensing blade. It senses touch via capacitive touch sensing, and these blue electrodes are 3D printed with conductive TPU. And the power and signal are transmitted via the slip ring that connects the top spinning assembly and the bottom static part. And each interface will be sliced along radial and angular axes. And what's more interesting and challenging is to know the touch location on the angular axis. It does so by measuring the time elapsed from the start of the current revolution and mapping that time to a slice number. At 550 RPM, for example, each revolution takes about 0.11 seconds. And with 180 slices of our resolution, each slice takes about 605 microseconds. So during this very brief interval, motor is spinning, electrodes are on motion, which introduces a lot of noise, physical contact is unstable, and the touch sensing window is extremely short and intermittent. So therefore, the goal is to make location sensing work for such transient, unstable touches, and our system needs to be fast. I'm going to highlight just a few key software implementations, and the full list is in the paper. So one challenge was that the touch events blocked code execution, causing the display to glitch whenever a touch occurs. To address this, we had to use a dual-core microcontroller to allow display control and touch sensing to run in parallel on separate cores. And on the noise control side, motion creates significant noise, and an effective technique we use to reduce such noise, the effect such noise, is to recalibrate the sensor after the rotation stabilizes. And by doing so, the system learns the baseline that already accounts for the spinning state. And there's more, please refer to the paper for more details. So what can we do with this technology? We show how BloomBeacon augment objects with limited surface area. So here I simply place our device on this basic speaker. And then it turns this basic speaker into a fancy vinyl player that displays the album cover. And I can also switch songs by touching the mid-air display. And it is an on-demand vinyl player. After I'm done with it, the device can be picked up and repurposed for different application. And let's repurpose it into the map augmentation to overlay weather information and the switch between the weather and the heat map. And the graspable form factor allows it to be easily moved to different locations on the map to show different relevant information. And finally, the line-like form factor makes it easy to store along linear elements, such as the edge of a shelf. So here I'm trying to reach inside for a potion without gloves. And then the device blooms into a physical surface that blocks the physical access. And after I put on the gloves, I acknowledge it, and now the space is clear. So even if our device is safe and allows a range of applications, an important question would be, how do people actually like and accept such a spinning display? And we answered this question through our user study. After letting participants try it themselves, we asked them to rate responsiveness, comfort, confidence, and enjoyment, and that their experience with the device is actually pretty positive. And we also changed rotation speed and electro height and see how they affect the experience. And here's the result. What's interesting is the result of the height change. We can see that among the three heights, the experience is consistently better with the increasing height. And this was also reflected from our participants' quote, who described it as the less fear, the most fun, like flappy wings, the most comfortable. And this also validates our electrode design. And lastly, I like to report the touch accuracy. So this is the system accuracy under highly controlled touches at different speeds and electrode height. And you can get the overall view of the system accuracy from this visualization. And in reality, the user touches are pretty diverse and wild. So with the statistical analysis, we found how speed and height affect the two important aspects of touch sensing, spread and offset. Speed effect on spread is significant, where the slowest has the least spread. And on the other side, height has significant effect on offset. So offset is this global shift of spread, and the highest electrode exhibit the least amount of offsets. And these findings are generalizable beyond a single device implementation. So future work, right now the deployment is from a line to a surface. And we see the possibility to further collapsing it into a dot, to go from a dot into a surface. And for this system, another exciting future work lies in context-aware activation and interaction. When BloomBeacon is placed at different locations, it can potentially show context-relevant interfaces. While these directions are immediate next steps for BloomBeacon, They also point to my broader research vision, empowering people to effortlessly and non-invasively augment and enrich their everyday environments. So that's all. Thank you for listening. We have a demo at booth 1188. The next and the last demo session is on Thursday 4:30, which is very fun and you must try it. You must not miss.